Good evening. We are Group H2, and we are comprised of Melissa Lichtenwald and Christopher Stevens. Tonight we're going to be talking about approximations to the probability of waiting. In general, when we're looking at a call center process, the first thing that happens when a customer call is initialized is you have to route the call to the appropriate customer service representative, or CSR. This is done using the customer input on what they want out of the call. Today, we see software being used quite a bit to help direct the call to the appropriate CSR. Now, different types of CSRs could handle service, or they could help a customer with ordering a product. In general, there are two types of call center. The generic or low skill level call center, where basically the CSR is asked to read a script and doesn't really deviate from helping a customer in a very standard way. Now, if the problem is more complicated than the CSR is trained, the problem just doesn't get solved. There's also skill-based CSR support, where different customer service reps are trained in different areas to help customers with different problems. Today, we're seeing an increased use of automated voice software to help call centers lower their costs and help route the calls in the most efficient manner. By using this automated voice software, they don't have to pay someone extra money to be working, and they can keep their utilization and their hiring rates lower. Some of the key issues in a call center are how many layers should we have. By layers, I mean you have the CSR at the front line, then you have a manager, then a senior manager, then maybe you even have something even higher to help customers with especially complicated issues. The other question you have to address is how many CSRs are needed and at what skill level. Obviously, at a higher skill level, the CSRs are going to cost you more money, and they may have different times to help customers solve their issues. All of this should be taken into account. Finally, you should consider what are the protocols for passing a customer or escalating their problem to a higher CSR. The pros of escalating it is that they may solve the problem much quicker and yield a much higher satisfaction for the customer, but on the downside, those higher level CSRs are going to be more expensive. In general, all of the queues we'll be looking at today very nearly resemble an MMS queue. Customers are going to arrive according to a Poisson process where the service times are exponentially distributed, and large systems are going to perform very well at high levels of utilization. The first approximation we're going to look at is the normal approximation. This is perhaps the most widely used, and it works for a wide variety of different situations. Here we'll use phi of z, which is the standard cumulative normal distribution evaluated at the statistic z. Here what we're looking at, though, is as the number of servers increases, the difference between the probability that you're going to get by this normal approximation and the exact value is going to decrease. And what this means is as you have a high number of servers, you're going to actually get a worse and worse approximation. These are the equations used to calculate the probability of waiting in the normal approximation. Here we see z, which is basically the number of servers minus 0.5 minus r, where r is basically lambda over mu. I'll now pass it on to Melissa. Oh, no, I won't. But as we also can see from this Excel output, what happens when you have a lower number of servers, say around 70, which is even somewhat high, and a high lambda, and a mu and a theta, and a mu, or a service rate that's pretty average, and a theta which we're actually going to ignore in the normal approximation, is that the best approximation is the normal. And in general, whenever you have a low amount of servers, this normal approximation is going to be best. I'll now pass it on to Melissa Lichtenwald to talk about the Halfin-Whitt approximation.
Thank you, Chris. The Halfin-Whitt approximation is best used when the number of servers is very high. This approximation is generally used when the arrival rate, lambda, and the number of servers, s, are increased such that the utilization of the system is very close to 1. Since the system with a large number of servers will be more robust to changes of the arrival rate than smaller systems, the Halfin-Whitt approximation is best suited to approximating the true probability of waiting when the number of servers is higher than about 80. Here's the equation for the probability of waiting for the Halfin-Whitt. This is very similar to the normal approximation, but instead it takes into account beta, where beta is equal to s minus r over the square root of r. As we can see from these excerpts from Excel, the Halfin-Whitt approximation nearly imitates the true probability of waiting value. Indeed, the Halfin-Whitt equation is much more closely matching the true probability of waiting value over the other approximations used in this example. We note here that the number of servers is quite high, which makes the Halfin-Whitt equation the best approximation to use. As we can see when comparing the normal approximation to the Halfin-Whitt approximation, as the rival rates increase, the Halfin-Whitt approximation is much closer to the exact approximation. This is shown in the bottom row, and at the higher rival rates, there is a big discrepancy between the normal and the Halfin-Whitt approximation. The Garnett, Mandelbaum, Reiman, or GMR approximation is used to approximate the number of customers who will abandon the queue after some amount of waiting time. This is the only of the three approximations that uses abandonment of the queue. All the others assume that if you enter, you will only remain in the queue until you are served. This approximation practically means that we will be able to have an arrival rate greater than the number of servers multiplied by the mean time needed to serve a customer. For any given number of servers, any mean service time, and any given arrival rate, the steady state conditions can be found. This is the probability of waiting equation for the GMR approximation. This takes into account beta, the same equation as found in the Halfin-Whitt approximation, and also h of x, which is shown here. And this also will include the abandonment rate. As we can see from these outputs, when the arrival rate multiplied by the number of servers is less than the arrival rate, the GMR approximation is the only one that can be used to approximate the actual probability of waiting. The normal and Halfin-Whitt equations, since they do not take into account theta or abandonment, return an error message. Thus, using GMR approximation is the most appropriate here. To sum up everything, the normal approximation is the most widely used and easiest to compute. For basic systems with small number of servers and little or no abandonment, this equation will likely be the most appropriate. For very high utilization levels and a correspondingly high number of servers in the system, the Halfin-Whitt approximation will yield the best approximation for the actual probability of waiting. The normal and GMR approximation may come close to the actual value, but the Halfin-Whitt approximation will come closest to the actual value. Finally, in systems where abandonment is common or the other equations will yield utilizations of 1 or greater, the GMR approximation is best. Here, theta helps us to represent the abandonment at each phase and means that we can achieve a steady state with any arrival rate and the number of servers multiplied by the mean service time. Thank you, and we really enjoyed taking IOE419.
Thanks!